The word tangent is derived from the Latin word tangens, which means touching. So a tangent to a curve is a line that touches the curve. A line joining 2 points of a curve is called a secant line. The secant to the function f of x to the point a f of a and x f of x is the line passing through this point. Its slope is given by m equal f of x minus f of a over x minus a. So what does that look like on a graph? So here we are given a graph and the secant line passing through 2 points a f of a, x f of x. So then the slope of the secant line, let's call that LS. So the slope of the secant line is equal f of x minus f of a divided by x minus a. We can approximate the equation of the tangent line using the equation of the secant line as follows. So consider this graph that we given here, let's call that f of x, and we want to estimate the equation of the tangent line that passing to the point x naught. And let's call this x naught. Let's go ahead and draw the tangent line. Okay, and I'll call that LT for tangent line. Okay, so let's say I'll go ahead and draw a couple of secant lines that is passing to 2 points close to x naught. So I can have, here's a tangent line. This is parallel with x naught. Not parallel, but it is a tangent line. Okay, that passing to that 2 point. And let's say if I choose another tangent line that is passing to the point x naught, f of x naught, and closer to x naught, f of x naught, and you can see that the secant line is slowly going closer and closer to the tangent line. Okay. And let's call that this value is x naught plus 8. So as x naught plus 8 become closer and closer to x naught, the secant line that passing through the point x naught, f of x naught plus 8, f of x naught plus 8 will be closely become the equation of the tangent line itself. So how do we write that down? So let L of S be the secant line pass through the 2 points x naught, f of x naught, and x naught plus 8, f of x naught plus 8. Then as 8 approaches 0, x naught plus 8 approaches x naught. This means the secant line approaches the tangent line. Now it does not become the tangent line, it be approximate of the tangent line. Find the equation of the tangent line to the parabola y equal x squared minus 4x at the point 1, negative 3. We will estimate the slope of the tangent line based on the slope of the secant line. And we will start by let L of x be the secant line passed through the point. One negative 3 and 1 plus 8 f of 1 plus 8. Then the slope of the secant line is equal f of 1 plus 8 minus f of 1 divided by 1 plus 8 minus 1. So 1 plus 8 square minus 4 times 1 plus 8 minus f of 1. So that is 1 square minus 4 times 1. Simplify the denominator, equal 8. This equal to 1 plus 2/8 plus 8 square minus 4 minus 4/8 plus 3 divided by 8. Simplify this, we get 8 square minus 2/8 divided by 8. Factor out an 8 in the numerator. Simplify, we get 8 minus 2. Okay, so this is the slope of the secant line. So to estimate the slope of the tangent line, this is what happened as 8 go to 0. Then the slope of the secant line is approximate the slope of the tangent line, and that is negative 2. The tangent line passes into the point 1, negative 3 and have the slope of negative 2. So then we can set up the equation as follows. We use y equal mx plus b. This means negative 3 equal negative 2 times 1 plus b. So b is equal to negative 1. So then the slope of, so the equation for the tangent line is approximate y equal negative 2x plus 1, minus 1. We use the same procedure to find the equation to the tangent line of the curve y equals square root of 7 minus x at the point negative 2, 3. So let L of x, let Lx be the secant line passes through negative 2, 3 and negative 2 plus 8 f of negative 2 plus 8. The slope of the secant line is equal f of negative 2 plus 8 minus f of negative 2 divided by negative 2 plus 8 minus negative 2. This equals square root of 7 minus negative 2 plus 8 minus 3 divided by 8. So this is square root of 9 minus 8 minus 3 divided by 8. To simplify this, we need to multiply the numerator by the conjugate. That is square root of 9 minus 8 plus 3 Okay. So now the numerator become 9 minus 8 minus 9 divided by 8 times square root of 9 minus 8 plus 3. Numerator become negative 8 This simplify to negative 1 over square root of 9 minus 8 plus 3. So as 8 go to 0, the slope of the secant line become negative 1/6. Okay. So then the slope of the tangent line is negative 1/6. So the tangent line pass into the point negative 2, 3 and have the slope of negative 1/6. So then y equal mx plus b. 3 equal negative 1/6 times negative 2 plus b. So this is 3 equal 1/3 plus b. So b equal 1/3. So the equation of the tangent line is y equal negative 1/6 x plus 8 over 3. Next, we talk about the velocity problem. Let's talk about the average velocity. S of t, let S of t be the position of an object moving along a coordinate axis at time t. Then the average velocity of the object over time interval at, where a is less than t, or ta if t is less than a, is given by v average equal s of t minus s of a divided by t minus a. As t approaches a, the average velocity becomes closer to the instantaneous velocity. So the instantaneous velocity, this means the velocity at the particular point in time. Okay. Let's take a look at an example. Suppose that a ball is dropped from this upper observation deck of the CN Tower in Toronto, that is 450 meters above the ground. The position of the ball is given by the equation S of t equal 4.9 t squared. Find the average velocity of the ball at the following time interval. Press A. So first interval, V is equal to S of 6 minus S of 5 divided by 6 minus 5. This is 4.9 times 6 squared minus 4.9 times 5 squared divided by 6 minus 5. This is 53.9 meter per second. For the time interval 5 to 5.5, S of 5.5 minus S of 5 divided by 5.5 minus 5. Plug this into your equation. You get 51.45 meter per second. And for the third interval, we get 50.225 meter per second. Find the velocity of the ball at t equals 5 seconds. We can do this by calculating the average velocity in the small interval as t come closer and closer to 5. So part B. Let's take a look at the time interval 5 and 5.125. Then the time interval 5.06. We can calculate the average velocity as the 5.125 minus s the 5 divided by 5.125 minus 5. Plug into the formulas, we got 49.61. The next one, we do the same thing. So this get us about so it seems like as t go closer and closer to 5, the velocity, the average velocity is about 49. So then the velocity at t equals 5 is approximate about 49 meters per second. In the next problem, estimate the instantaneous rate of change of g of t equal 2 over t minus 3 at the point t equal to negative 1. So the rate of change is the slope. So in other words, we want to estimate the slope of the tangent line that passed to the point t equal negative 1. In order to do that, we will calculate the slope of secant line that are close to negative 1. We will use that to estimate the slope of the tangent line from there. So to calculate the slope of the secant line close to negative 1, we first will make a chart. The value of t that are close to 1. And we calculate the value of t. So we plug in t into the equation g of t equal 2 over t minus 3. At negative 0.8, g of t equal negative 0.5263. Negative 0.5. We will use this to calculate the slope of the secant line. So in the first secant line, This is the interval for time negative 0.9, 0.8 to negative 0.9. We use the formulas negative 0.5, 1, 2, 8 minus negative 0.5263 divided by negative 0.9 minus negative 0.8. This gives us negative 0.1349. We do the same for the next couple pair. And we get the results as follows. So the instantaneous rate of change at the point t equal to negative 1 is somewhere between negative 0.1282 and negative 0.121. So let's go ahead and take the average. The area problem in integral calculus. We can calculate the area basic figure such as triangle and square. So what if we want to calculate the area under a curve? We can approximate the area by dividing up the interval AB into smaller interval in the shape of rectangle. The approximation of the area comes from adding up these area of this rectangle. So let's say we want to estimate the area under the curve of f of x equals x squared plus 1 over the interval 0 to 3 by using 3 rectangles. First, we will draw the curve over the interval 0, 3. When x equals 0, f of 0 equals 1. And when x equals 3, f of 3 equals 10. So we have this curve, and this is not to scale. I then will draw in partition the area under the curve into 3 areas. Now, first one, we can estimate the area under the curve using this rectangle. The sum of this rectangle. We estimate the area under that curve. Note that this is an underestimate. So the height of the rectangle is at f of 0, f of 1, and f of 2. The width of the rectangle is 1. So the area under this curve is the sum of this rectangle. So f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. And this is underestimate. Let's try this again using the different rectangle. So here's the curve, same curve. And we still partition the area under the curve into 3 sections, 1, 2, and 3, using 3 rectangles. So let's say, what does the area look like if I draw the rectangle differently? If I use this point, these are the rectangles that I'll be using, then clearly this is an overestimate. The height of the first rectangle is f of 1. The second rectangle is f of 2. And the last one is f of 3. Well, I'm not exactly happy with the way we have a rectangle. We have an underestimate, we have an overestimate. I want something a little more accurate. So let's partition the rectangle in a different way. So here we have the curve still, right? And we still go from 0 to 3. Let's say if I draw the rectangle using the height is the midpoint between 0 and 1. The midpoint between 1 and 2. Then the midpoint between 1.5 and, the midpoint between 2 and 3. I still can estimate the area under the curve, but it looks a little more reasonable, closer. The area is a little closer to the actual area. So to do that, so this method called using the midpoint. Okay. We partition the curve, we partition the interval to 3 intervals, and we find the midpoint of each interval. So the partition it in 3 intervals from 0 to 3. We get the first interval is 0 to 1, 1 to 2, and 2 to 5. The midpoint will equal to 0.5, 1.5, and 2.5. Note that the width for this rectangle is still the same, that is 1. So this is a little more accurate area. So the area is still f of 0.5 plus f of 1.5 plus f of 2.5. Let's say what happened if we use SID rectangle, and this time I'll use the midpoint. First of all, we take a look at the interval from 0 to 3. We divide it into SID. So 3 minus 0 divided by SID equal 1 over 2. So SID 0.5, 1.5, 2.5. And if I want to use the midpoint, then the midpoint in the first interval, from 0 to 0.5, this is 0.25. The next one, 0.5 to 1, that is 0.75. The next partition, 1 to 1.5, this is 1.25. 1.5 to 2, this is 1.75. So this is 0.25, 0.75, 1.25, 1.75. The next one is 2.25, and the last one is 2.75. Note that since we use sit rectangle, the width of each of this rectangle is 1/2, not 1. So then the area equal 1/2 times f of 0.25 plus 1/2 f of 0.75 plus 1/2 f of 1.25